Okay, so I'm uploading this video to give you some help on reviewing for exam number 3. This is typical of what we did on the first 2 reviews. This is not a copy of your exam. Your exam will be a week from Tuesday after spring break, and the instructions will come later. But this is a recap of some of the main topics that we've covered. And how are you going to study for this exam? Practice problems, go over the material, the results that you need to do those problems. If you need to, go over your notes and rewatch some of the videos. Okay, so let's start. Your exam is going to start on section 9.1. In section 9.1, we talked about sequences and whether they converge or diverge. And all it means for a sequence to converge is that the limit, as n goes off to infinity or as k goes off to infinity, exists, right? And so find the general term of the sequence starting with n equals 1, determine whether the sequence converges. And if so, find its limit, right? And so here we're looking for pattern recognition. And so what you notice is that each term, these are your terms, the first term, second term, third term, fourth term, has 2 fractions. The first one doesn't look like a fraction, but if we write it as 1 over 1, we're good. And then we have 1 over 1 minus 1 over 2, and then 1 over 3 minus 1 over 2, and then 1 minus 3 minus 1 over 4. And to help us look for a pattern on this one's a little tricky. It's not obvious, but if we factored out a minus from this one, we would have 1/2 minus 1/3. And this one we'll leave alone. And then this one will factor out a minus. And again, what I really encourage you to do is not to just sit here and watch these videos, but pause the video as soon as you think you can do it. So you might start the video, try the problem on your own as soon as I show you the slide. You're a little stuck, so watch a little bit of the video. And so maybe you couldn't do it then because you couldn't figure out what to do. But now that you see this, now maybe you can. So when we went over this in class, what's going on here is you have this factor of -1, right? And so then a sub n, see, here's a 1, here's a -1, here's a 1, here's a -1, and we saw those. You were going to need a factor of -1 to the n, but since we want to start with a positive 1, we want to do an n plus 1 because we're starting with n equals 1, right? Now, again, that takes care of the plus, minus, plus, minus. Now let's take care of the first fraction. And the first fraction is 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4. Right? Just looking at it term by term instead of looking at the whole thing. And then what we see is we get 1 over n. Minus the second fraction is 1 over, first it's 2, then it's 3, then it's 4, and then it's 5. So that's just n plus 1. Okay. And now each of these terms go to 0 as n goes off to infinity. So the limit as n goes off to infinity of -1 to the n plus 1 times 1 over n minus 1 over n plus 1 is 0. Right? And so again, we talked about sequences and series And we talk about both of them converging, and you can't confuse the two. This is just a sequence. We're just looking at the individual terms. We're not adding them up yet. But that sequence converges because each of those 1 over n and the 1 over n plus 1 goes to 0. And so when we're subtracting them, the whole thing goes to 0. So it converges, and the limit is 0. Okay, then we went over increasing and decreasing. Increasing is A1 is less than A2, which is less than A3. And decreasing is A1 is bigger than A2, which is bigger than A3. And so a sequence that is either increasing or decreasing is said to be monotone. And a sequence that is either strictly increasing or strictly decreasing is said to be strictly monotone. We're not going to be too concerned with strictly. As long as it's increasing or decreasing, we're okay. We're really going to only need one test for monotonicity. We're going to use the ratio test, right? The ratio test, we're going to take a term and divide it by the term before it. And if we can show that's always greater than 1, then if you multiply both sides by an plus 1, then an plus 1, by an will be bigger than an. And that says that any term is bigger than the term before it. And if it's less than 1, then that'll say, so that means that it's increasing. The terms get bigger. And an plus 1 over an being less than 1 means that it's decreasing, right? And so this is one way of showing increasing. This is especially useful when you have, when your sequence is defined using things that we can't differentiate, like a factorial. You can't take the derivative of that, but you can use the ratio test to show that it's increasing or decreasing. Okay, so in this problem, it says use the ratio a sub n plus 1 divided by a sub n to show that the given sequence is strictly increasing or strictly decreasing. We're not going to worry about strictly. We're not going to worry about the strict inequality. So again, what you should see here is that a sub n is 10 to the n over 2n factorial. And so then we need to compare that with a sub n plus 1, which is the term that comes after a sub n. And then to do that, to find that, we just go and we replace n with n plus 1. And so you get 10 to the n plus 1. And then 2 times n plus 1, which is 2n plus 2 factorial. And then we're just comparing these two terms, an plus 1 to an. And so we always take the a sub n plus 1 and divide it by the term before it, a sub n. And so then you're going to take the 10 to the n plus 1, and you're going to divide it by 2n plus 2. And multiply it by the reciprocal of a sub n, which is going to be 2n factorial divided by 10 to the n. And then we clean that up, and we want to compare that to 1 after we clean it up. To clean it up, you have the same base right here, so you subtract the exponents and you just get 10. To clean up the factorials, the bigger factorial is on the bottom. So we break off factors until we get to the smaller factorial. So 2n plus 2 factorial, your first factor is whatever number this is, 2n plus 2. Your next factor is 1 less than that, so 2n plus 1. Your next factor is 1 less than that, so 2n. But then that matches the 2n factorial that we have right there. So rather than continuing, we just put 2n factorial, and we have the 2n factorial. And then these go away. And so then we get 10 over 2n plus 2 times 2n plus 1. Okay, but n starts at 1 and just gets bigger. So this expression just is getting bigger. So at 1, we get 2 plus 2, which is 4. And here we get 3. 4 times 3 is 12. And so then 12 is bigger than 10. So 10 over 12 is less than 1. And for n equals 2, 3, 4, these numbers just get bigger. So it should be pretty clear that 10 divided by 2n plus 2 times 2n plus 1 is going to be less than 1 because this number will be bigger than 12 and the number on top stays fixed at 10. So since this is less than 1, therefore decreasing. Okay, so notice that this does kind of look like the ratio test, but this isn't the ratio test. We are determining whether our sequence is increasing or decreasing, and we do that by dividing a sub n plus 1 divided by a sub n. There's no limits here. Please don't take any limits. All this says is that no matter what term you pick, if you divide it by the term before it, you will get something that's less than 1. And so then that means that a sub n plus 1 is bigger than smaller than the a sub n, which means it's decreasing. Okay. We could also use differentiation to show that that a sequence is increasing. If I tell you how to do it, you can do it that way. So we can use our first semester calculus. The only difference between a sequence and a function is that for the sequence, we're only allowed integer inputs, and for a function, you're allowed any real value inputs that are in the domain. So we look at the corresponding function, f of x equals n times e to the negative 2x. I'm sorry, f of x. Right. So when we use n, we're implying that our input is an integer, and we can't do calculus on sequences. So we replace it with the corresponding function, right? And then we find the derivative f prime of x. This is a product, so we use the product rule. The derivative of the first one is 1. The derivative of the second one is e to the negative 2x. Okay. Plus. Then we leave the first one alone, x, and take the derivative of e to the negative 2x. But e to the negative 2x is a composition. So we use the chain rule. The derivative of the e to the function is the e to the function with the same inside, and then we multiply by the derivative of the inside. Okay. Finally, we can clean this up by factoring out an e to the negative 2x, which then leaves behind 1 minus 2x squared. Okay, and now what you should know is that this expression here is always positive, right? And so then the only thing that is going to determine whether your first derivative is positive or negative is this factor right here. Now this doesn't factor very nicely, so we can just figure out what are the zeros of this part. And so we can figure that out on our own. Separately over here, we want 1 minus 2x squared to equal 0. And so then 1 will have to equal x squared. So then 1/2 will equal x squared. So then x will equal plus or minus 1 over the square root of 2. And 1 divided by the square root of 2 is less than 1, right? And so then we can make the sign chart for the first derivative. But again, we are only interested in values that are bigger than 1. So we don't need the negative 1 over the square root of 2. 1 over the square root of 2 is over here. And then we're only interested to the right of 1. But to the right of 1 over the square root of 2, your output will either always be positive or always be negative because we have a continuous function. And so then the only places where it's 0 are at 1 over the square root of 2 and negative 1 over the square root of 2. So in each interval, it is either always positive or always negative. And how do you figure out which one it is? You pick a number in that interval. We're going to go ahead and pick 1, plug it in. Of course, this expression is always positive, so this is all that matters. And when you plug in the 1, you get negative 2. So when you take f prime of 1, you get negative, no, I'm sorry, not negative 2, negative 1. So 1 squared is 1 times 2 is 2. 1 minus 2 is negative 1. And so that means over here it's decreasing. And what the first derivative tells you is it tells you whether the original function is positive or negative. So what we see here is that f prime of x is less than 0 for x greater than 1. Therefore, n e to the negative 2n is decreasing. Okay. Use differentiation to show that the given sequence is strictly increasing or strictly decreasing. It's decreasing. From there, we went on to section 9.2. And in section 9.2, we started talking about series. And what we're doing with the series is we are trying to figure out whether this infinite sum converges. And what does it mean to converge? It means that as you add more and more terms, your sum is getting closer and closer to something. And so since you have an infinite series, then since you have an infinite sum, a very common theme in math is to take a new problem and turn it into an old problem. And so there are only 2 types of series that you will be able to find the actual value for on this test, right? And those are telescoping series, where you can come up with a formula for the nth term of the partial sum, or for the geometric series, where you have a formula for that already, right? So your instructions here are to write out the first 5 terms of the sequence of partial sums for the infinite series, and then to find the sum. Okay, so telescoping series, you're going to want to have a sequence of partial sums where some of the terms start canceling out after a moment, right? So when you just have one fraction here, it's going to be difficult to figure out to see that as a telescoping series. So instead, we want to take this 1 over k squared minus 1, and we want to rewrite it as a sum of 2 fractions and hope that it telescopes. Now, because I'm asking you to find the sum, then you should know it's going to telescope. Okay, so we know that this has to break up as 1 over k minus 1 and something over, I said 1, a over k minus 1 and something over k plus 1. And if we clear the fractions, we will get a is equal to, 1 is equal to a times k plus 1 plus b is equal, plus b times k minus 1. So we're just using partial fraction decomposition so that we can rewrite our one term in two terms so that we can see the telescopingness of it. So if we let k equal -1, then if we let k equal -1, then this will go away and you will get -2b equals 1. And so then b is equal to -1/2. If we let k equal 1, then this term will go away and you will get 2a equals 1. And so then a is equal to +1/2. And so then that tells us that the 1 over k squared minus 1 can be rewritten as 1/2 over k minus 1 minus 1/2 over k plus 1. Okay, so I'm going to erase all this because I need more space. So you go through the partial fraction decomposition. So that you can rewrite your series as the summation from k equals 2 to infinity. Now notice that we have these common 1/2 here, and because of our limit laws we can take this 1/2 out because they both have a factor of 1/2. We can take that out and we have 1 over k minus 1 minus 1 over k plus 1. Now what should tell you that this is going to telescope is that we're starting at 2, is that because this one is k minus 1 and this one is k plus 1, as we move forward, some of the terms are going to eventually be the same and then cancel out, right? So now if you're good with this, you don't need to do what I'm about to do, and you can just write down your formula for S sub n. But the way I found it the easiest to write your formula for S sub n is to write out the first 5 terms of the sequence to see how this works. So the sequence of partial sums is you're starting at 2, and you put in your 2 into your formula, and 2 minus 1 is 1. You get 1 minus 1/3. Don't clean it up, just leave it alone. S2 is this 1 minus 1/3 plus the next term. And the next term is going to be when you plug in 3. 1 over 3 minus 1 is 2. Minus 1 over 3 plus 1, which is 4. So this is k equals 3. This one's k equals 2. Okay. Nothing cancels out. Nothing is happening yet. S3 is where the magic begins. 1 minus 1/3 plus 1/2 minus 1/4. And then when k equals 4, then you're going to get 1/3 minus 1/5. And you see now that now stuff is going to start canceling out. So these 1/3 are going to cancel out. Okay, and so now S4 we can keep those 4 terms that didn't go away. 1 plus 1/2 minus 1/4 minus 1/5. Looks like I'm going to need more space. And so S4, what's left is 1 plus 1/2 minus 1/4 minus 1/5. And then you're going to substitute in what you get when k equals 5. And when k equals 5, you get 1/4 minus 1/5. I'm sorry, minus 1/6. K is 5. So 5 plus 1 is 6. And you can see now that the quarters go away. And so when you go and find S5, now you have 1 plus 1/2 minus 1/5 minus 1/6. And then you add the next term, which is when k is 6. So you get 1/5 minus 1/6. So no, I'm sorry, k is 6, 1/7. So then the 1/5 will go away. This is k equals 6. So 6 minus 1 is 5, and then 6 plus 1 is 7. Okay, so from there, you can see that this is going to continue to go on. Every time you add one more term of the series, what is going to happen every time you add one more term of the series, one of the terms that you had before is going to go away. And so then you will always have 4 terms. So starting with 2, you start to have 4 terms. And so it looks like Sn, the sum of the first n terms, is you're always going to have a 1. You're always going to have a 1/2. But then when n is 2, the other terms are 3 and 4. When n is 3, the other terms are 4 and 5. When n is 4, the other terms are 5 and 6. And when n is 5, you have 6 and 7. So then for n, your other 2 terms will be minus 1 over n plus 1 minus 1 over n plus 2. So now we found a closed form formula for the sum of the first n terms. And so now the way we can now find our sum, the infinite sum, is by taking the limit as n goes off to infinity of the S sub n. And when we do that, these go to 0 and you get 3/2. And so that is your sum. So the summation from k equals 2 to infinity of 1 over k squared minus 1 is equal to 3/2, which means that this infinite series converges. And all that means is as you add more and more terms, then you just keep getting closer and closer to 3/2, right? That's all that means. And so then we're going to define the infinite sum to be 3/2. Now, then another special kind of series where we actually know what the sum is when we have a geometric series. The important thing to know about a geometric series is that you get from one term to the next by multiplying by the common ratio. So memorizing this formula right here doesn't really matter too much. What you need to notice is that when you write it out, you get from one term to the next by multiplying by the common ratio, and that would be r. And how do you find the common ratio? You take your a sub n plus 1, you take any term and divide it by the term before it, and it should equal r. Now, if your r is bigger than or equal to 1, or I'm sorry, if the absolute value of your r is bigger than or equal to 1, then your series is going to diverge. But if the absolute value of your r is less than 1, then not only do we know what it converges, that it converges, we know what it converges to. It will always converge to the first term, all divided by 1 minus the common ratio. So we know that the series converges, and we can find its sum. A lot of the series that we came across in our later sections, we don't really know what they converge to. We only know that they converge or diverge. But when you can find a closed form formula for your series, I'm sorry, for your sequence of partial sums, then you can take the limit and find your sum. And for a geometric formula series, we don't have to do that. We have a formula for all of them. Okay. Determine whether the series converges, and if so, find its sum. So you should recognize that because of the exponent here, this is a geometric series, right? Your base is constant, your variable is in the exponent, and this is a geometric series. If you don't see that, then what you could do is write out some of the terms, right? So when you start with 1, you get 2/3 to the 3 power, plus when you put in 2, you get 2/3 to the 4th power. When you put in 3, you get 2/3 to the 5th power, and so on. And this series goes on forever and ever. Now, you should notice that you're getting from one term to the next by multiplying by 2/3. So that makes it geometric. And when it's geometric, you look at your common ratio. What number are you multiplying by to get from one term to the next is 2/3. And 2/3 is less than 1. Therefore converges. And not only do we know that it converges, we know what it converges to. It converges to the first term, and this is your first term, which is 2 cubed is 8, 3 cubed is 27, over 1 minus the common ratio, 1 minus 2/3, which is 8 over 27 and 1/3. And multiply top and bottom by 3, and you get 8 over 9. We also learned in section 9.2 a very important result that gets misunderstood. It tells you if the series converges, then the terms have to go to 0. It doesn't tell you if the terms go to 0, then the series converges, right? The harmonic series, 1 over k, the terms go to 0, but the series diverges. Right? So this idea that if the terms go to 0, then the series converges is not correct. And here's a counter example. Okay, but it is a very useful test. On this one, might be useful to write out the terms, right? So when k is 1, you get the sine of pi over 2, which is 1, plus, when k is 2, you get pi, which is 0, sine of pi, which is 0. When k is 3, you get the sine of 3 pi over 2, which is negative 1. And when k is 4, you get the sine of 2 pi, which is 0. And when k is 5, you get the sine of 5 pi over 2, which is 1. And so what you're really doing here is your argument of the sine function, what you're taking the sine of, is you're just bouncing around from pi over 2 to pi to 3 pi over 2 to 2 pi to 5 pi over 2 to 3 pi, and you're just going to be bouncing around here. And so then you can see that this is always going to be 1 plus 0 minus 1 plus 0 plus 1, and then plus 0, and then minus 1, and it's just going to go on and on forever and ever. And so then does the series converge? No. The limit as k approaches infinity of the sine of k pi over 2 does not equal 0, right? The limit does not exist. And since the limit doesn't exist, it doesn't equal 0. So if you can show that the terms do not go to 0, then you know that your series diverges. And that's what's going on with this one. But just because your terms go to 0 does not mean that your series converges. The harmonic series tells us that. Now, so then in the remainder, well, not in the remainder, but in the next few sections, we're only interested in determining whether a series converges or diverges, not what it converges to. And so one of the things we have is the integral test, right? And so basically, if the corresponding improper integral converges, then the series converges. If the corresponding improper integral diverges, then the series diverges. As long as your sequence, as long as your series is decreasing and your corresponding function is continuous. Okay. As long as your corresponding function is decreasing and continuous on the interval, then you're good. Okay. So you may or may not be told how to do the problem. If you are not told how to do the problem, then you can do the problem however you like. If these are the instructions, determine whether the series converges. We've gone over numerous tests to help us with that. But if you look at this, you can realize that if I were doing the antiderivative of the natural log of x divided by x dx, this integral wouldn't be too hard to do, right? Because this is a u substitution. U would be the natural log of x. Du would be 1 over x dx, and then that would be a pretty basic integral. But we're taking this from 3 to infinity. And before we use this, we have to make sure that my series is positive, decreasing, and continuous, right? So it's clearly a positive. There's no way for a negative number to come in when you're natural logging and dividing by the number. Once you use numbers bigger than 3, it's positive, right? So the natural log of x divided by x is clearly bigger than 0 as long as x is bigger than 3. Right? So for decreasing, we could use the first derivative test because the ratio is going to be too hard to do. So we could just use the derivative test. F prime of x is equal to, here we have a quotient, so we need the quotient rule. Derivative of the top is 1 over x. Bottom left alone, x minus, leave the top alone, natural log of x times the derivative of the bottom, 1, all over the bottom squared. And so then this is 1 minus the natural log of x, but again, x is bigger than 3, bigger than or equal to 3. And then down here you have x squared. Now the bottom is always positive, and what you should know about the natural log function is that it's always increasing. So then once we get past e, it's 1. At e, it's 1. So then past e, which is, where we are, x is bigger than or equal to 3, and e is 2.7 something. And so then you get 1, and so then at 3, it's always bigger than 1. And so since the natural log is bigger than 1, 1 minus the natural log is less than 1. I'm sorry, less than 0. Therefore, decreasing. And so then we can look at this integral instead of this series, and if this integral converges, then this series converges. And we did this on the last exam. To determine whether this integral converges, we take the limit as b goes off to infinity of the definite integral from 3 to b of the natural log of x divided by x dx. We let u equal the natural log of x. Du is 1 over x. And we go and we make our substitutions. 1 over x dx, right? So then we end up with the limit as b goes off to infinity of the definite integral from 3 to b of the natural log of x becomes u, dx over x becomes du, and there we go. This has a pretty simple antiderivative. This becomes the limit as b goes off to infinity of the limit as b goes off to infinity of u squared over 2. We can bring out the 1/2 over here, evaluated from 3 to b. Okay, so then this is equal to 1/2 times the limit as b goes off to infinity of the natural log of x. I have to go back since I didn't change my limits of integration. I have to go back to x. Natural log of x squared evaluated from 3 to b, which is then 1/2 the limit as b goes off to infinity of the natural log of b squared minus the natural log of 3 squared. And because the natural log keeps growing without bound, and when we square it, that just makes it grow even bigger. This is infinity. Therefore, your series diverges. Okay. So we did all that work, and we showed that it diverges, right? But let me show you why we went over some of the other tests. This one is, when you can do the integral, it's pretty straightforward. But what you should know just by looking at the graph, like we said earlier, you should know that the natural log of k is bigger than 1. And so then if we divide both sides by k, the natural log of k over k is bigger than 1 over k. But we know that 1 over k diverges. And so therefore, the bigger one also diverges. This is the basic comparison test. And do you see how quick that was? Now, if you're not comfortable with these, so it may be a little bit more difficult, but this is why we go over them. So when you get comfortable with them, you can do things a lot quicker. And there are some things that we just can't integrate. But I thought that was kind of nice that we had the integral test, which took a while, but this one was pretty quick. I just, realized that I made a mistake. So let's come back to over here. There was a 1/2 that I factored out. And so then this, so let me go ahead and erase this. So this was equal to, I factored out the 1/2, and we had the summation from k equals 2 to infinity of the 1 over k minus 1 minus 1 over k plus 1. And now my sequence of partial sums was just for this. So then we figured out that this limit was 3/2, but then this 3/2 needs to get multiplied by the 1/2. So the 1/2 times the 3/2 is 3/4. So that is my limit is 3/4. I'm sorry, my sum is 3/4, not 3/2, because I have that extra factor of 1/2. Okay. Let's go back to where we were. It's going in the wrong direction. Okay. We could use the integral test to prove this theorem, that when you have 1 over k to the p, then your series converges if your p is bigger than 1, and it diverges if p is between 0 and 1, including the 1, not including the, we don't call it a p series if it's just a 0, although that one would diverge as well, because it would just be 1. So again, the usefulness of this is that you have a series that's readily available, that you should be able to tell just by looking at it what it does. So in exercises 33 through 38, use theorem 911 to determine the convergence or divergence of the p series, right? So when you look at this, you may not recognize this as a p series because it wasn't written to you in summation notation. So what you might want to do is rewrite it in summation notation. This is why we spent that first time in section 9.1 going over how to write sequences. And so we'll start with k equals 1. And since it says ... we'll go infinity. Notice that each term except for the first one is a fraction, and if I wanted to, I can make it a fraction by putting a 1 there. Each term has a square root, and right there, 2, 3, 4. So if I wanted to, I could put that there, and that doesn't change anything because the square root of 1 is 1. And now, all of them are fractions where my numerator is 1. Look at the denominator and you have 1, 2, 3, 4, 5. So that's just k in front of the square root of 1, 2, 3, 4, 5, k. And that still doesn't look like a p-series until you realize that this is the summation from k equals 1 to infinity of, these have the same base, and you just add the exponents, and so you get 1 over k to the 3/2. So now your p is equal to 3/2, therefore converges. And we're done. Now in section 9.4, we went over a couple of comparison tests. So in section 9.4, we went over a couple of comparison tests, and the first one is the basic comparison test. So you have two series, A sub k and B sub k, and basically if the bigger series converges, then the smaller series also converges, and if the smaller series diverges, then the bigger series also diverges. These tests are a little bit challenging because they require some intuition, and you only get that with practice and experience. And there's no algorithm on how to do this, so we'll go through a couple problems here. So this says, use the comparison test to determine if the series converges or diverges. So again, the test or the previous slide had two series and you're only given one, right? And so then again, what you want to do is ignore all of the terms but the fastest growing terms in both the numerator and denominator. Well, the numerator is only one, so nothing really there. We're not a whole lot that we can do there. And so we're just going to have a 1. But in the denominator, we have that extra 2. And if we just ignore it, this is what you should compare it to. So you have to come up with your own series. And so then this right here is a P series. And you should know what P is. And again, so P here is 1/2. It being less than 1 means that this series diverges. Okay, so here's what's going on then. The square root of k minus 2, it should be very clear to you that that is less than the square root of k. And then when I flip it, 1 over the square root of k minus 2 is bigger than 1 over the square root of k. So we've just shown that the terms of this series are bigger than the terms of this series, and this series diverges. Therefore, the series of 1 over the square root of k minus 2 diverges. But sometimes that doesn't work out so well. So when the problems are a little bit tougher, rather than using the basic comparison test, we use the limit comparison test. So let A sub k and B sub k be series with positive terms, and suppose that the limit as k goes off to infinity of A sub k over B sub k is rho. If rho is finite and rho is greater than 0, then the series both converge or both diverge. So again, if you're not very comfortable with this, this might look like the ratio test. We're not using the ratio test here. There is a ratio, but you're not comparing the you're not comparing the terms of only one sequence. You're comparing the terms of two sequences. I'm sorry, two series. Okay, so keep that in mind. Use the limit comparison test to determine if the series converges or diverges. Okay, so again, it is very clear that 4 to the k minus 2 is less than 4 to the k. That should be clear to you. This one you're subtracting 2, that makes it smaller. But when I flip it now, you get 1 over 4 to the k minus 2 is bigger than 1 over 4 to the k. Now the 1 over 4 to the k you should recognize as geometric, and you should recognize that it converges. But because these are bigger, the basic comparison test doesn't hold, right? And so we could make it hold as I did on your video, but then it just becomes more complicated, right? So if I don't tell you how to do the problem, you can do it however you like. This tells you to use the limit comparison test, but I was showing you that the basic comparison, why the limit comparison test is important, because the basic comparison test is sometimes difficult. But when it's not difficult, it's pretty quick. So you should learn both. Okay, so again, what we should compare this to is ignore all but the fastest growing terms in the numerator and denominator. And so what we should compare it to is 5 over 4 to the k. Now we can factor out the 5, and this is just 1 over 4 to the k, or 1/4 to the k, and you should recognize that's geometric. And that it converges. Because your common ratio is 1/4, right? And so then what we're going to do is we're going to use the limit comparison test and take the limit as k goes off to infinity of the a sub k, and these will be the a sub k, and these will be the b sub k, and which one's a sub k and which one's b sub k does not matter, divided by b sub k. So then this will be the limit as k goes off to infinity of 5 over 4 to the k minus 2 times the reciprocal of 4 to the k over 5. These go away. And then what you have is the limit as k goes off to infinity of 4 to the k over 4 to the k minus 2. Okay, now this is not a rational function. You're not allowed to use the rational function results because it's not a rational function. You can use the idea of the rational function, and what we did is we looked at the bottom and multiplied by 1 over the largest power on the bottom, and so then we'll multiply the top and bottom by 1 over 4 to the k. And so then this will become the limit as k goes off to infinity of, and then on top we get 1, and then over here we get 1 minus 2 over 4 to the k. Now for this one, the top is staying fixed at 2 and the bottom is growing without bound, so that's 0. So this limit is 1. Now you need to be careful, right? You later learned the ratio test, and your ratio test tells you that if your limit is 1, the test is inconclusive. But this is not the ratio test. This is the limit comparison test. And for here, if rho is finite and greater than 0, then the series both converge or both diverge. So here, because it's finite and 1 is a perfectly good answer. The test is conclusive. Therefore, the series 5 over 4 to the k minus 2 converges. We moved on to talk about alternating series, series that go plus, minus, or minus, plus, minus, plus. And we have the alternating series test. AST is what I will write from time to time in these slides. And a series will converge by the alternating series test provided the two conditions hold. The first one is that your series is decreasing, the non-alternating part, right? So just looking at the absolute values, just looking at the absolute values, if it's decreasing, and if the terms go to 0, then your series has to converge. Right? Show that the series converges by confirming that it satisfies the hypotheses of the alternating series test. Okay, so here the a sub k are given to you by the formula. Let me write it up here. The a sub k that the theorem is talking about is given to you by the formula of k over 3 to the k. And this part right here just makes it alternate. And so so you get k over 3 to the k. So we need to show that it's decreasing. And using the derivative to show that it's decreasing would be a little bit troubling because we have a quotient. And yeah, so that's going to be difficult. So this is why instead I expect you to be able to compare a sub k plus 1 to a sub k. And a sub k plus 1 is just to go and replace k with k plus 1. And so then no limits here. We're just taking a sub k plus 1 and we're dividing it by a sub k. And that would be k plus 1 over 3 to the k plus 1 multiplied by the reciprocal 3 to the k over k. These k's go away. And what you end up with is k plus 1 over 3k. Now, it should be clear to you that if you take an integer, a positive integer, and add 1, and that will be smaller than if you take that integer and multiply by 3. That's what you're comparing now. 1 more than the natural number, and 3 times the natural number. And so then 3 times should be bigger, so the whole thing is less than 1, therefore decreasing. It's decreasing, it's alternating. Oh, we also have to show that the terms go to 0. So the limit as x goes off to infinity of x over 3 to the x is equal to, well, this goes to infinity and this goes to infinity. And so then you can L'Hopital it. And so then you get the limit as x goes off to infinity of the derivative of x is 1. The derivative of 3 to the x is the natural log of 3 times 3 to the x. And now the bottom is growing without bound and the top is staying fixed at 1, so your limit is 0. So therefore, since it's decreasing, alternating because of this, and the terms go to 0, converges by alternating series test. So then we talked a little bit about absolute convergence. So a series is said to converge absolutely if the series of absolute values converges, and is said to diverge absolutely if the series of absolute values diverges. And then we have this nice result, right? So sometimes we have series that alternate in sign, and our comparison test and our integral test only work for positive terms. So if we look at the series of absolute values, and if that converges, well, then it should make sense that the series with both positives and negatives also converges. And that's what this theorem tells you. So classify each series as absolutely convergent or conditionally convergent or divergent, right? So if we just look at the series of 1 over the square root of k squared plus k, just distributing, if this one converges, then we're done. It's absolutely convergent. If this one diverges, then it's we're still not done. We got to go and look at the top one and see if maybe that one converges by the alternating series test. And so again, if we ignore this k here, the term that grows the slowest in the denominator, we're looking at the summation of 1 over the square root of k squared, which the square root of k squared is just k, and this one diverges. Okay. Then you should have the instinct that this one diverges since since we can compare it to this one. And the question is, do we want to compare it with the limit comparison test or with the basic comparison test? So with the basic comparison test, it should be clear that k squared plus k, adding this k makes it bigger than k squared. And so then when I square root both sides, since the square root is a increasing function, the square root of k squared plus k is still bigger than the square root of k squared. And so then when I flip it, 1 over the square root of k squared plus k is less than 1 over k. That doesn't help, right? This one diverges. We need ours to be bigger and not smaller. And so we could adjust that, but that's too much. No need to do that. We have the limit comparison test. We're not told how to do this, so we'll just use the limit comparison test. The basic comparison test didn't work out. So we will take the limit as k goes off to infinity of the a sub k divided by the b sub k. This will be my a sub k, this will be my b sub k, which is then just going to end up being k over the square root of k squared plus k. We would like this to have a square root, so we can just square it and square root it. The square root of k squared plus, the square root of k squared is just k. We just rewrote it. But now that it's all one square root, we can take the square root all the way out, and this becomes the limit as k goes off to infinity of k squared over k squared plus k, and this is 1. Since that's finite and not 0, therefore both diverge. But we're not done. It says classify each series as absolutely convergent, conditionally convergent, or divergent. So we just showed that this is conditionally convergent. That this is divergent, but we don't know if the original one converges or not. But I'm not going to go through it. The summation from k equals 1 to infinity, you can see that the terms are going to 0. You can see that it is decreasing because the bottom is increasing, it just keeps getting bigger and bigger. And then terms are going to 0, decreasing, and it's alternating, converges by alternating series test. Therefore, conditionally convergent. So it converges, it just converges conditionally. Okay, so then we moved on to the ratio test. Let the summation of AN be a series with non-zero terms. The series converges absolutely when the limit as n goes off to the infinity of the absolute value of the a sub n plus 1 divided by the absolute value of the a sub n is less than 1. The series diverges when the ratio of the a sub n plus 1 to a sub n is bigger than 1, or if it's infinity, and the ratio test is inconclusive when it's exactly equal to 1. And so this is why we need the other test, is because when our ratio is 1, this test doesn't tell us anything. So use the ratio test. In exercises 17 through 38, use the ratio test to determine the convergence or divergence of the series. If the ratio test is inconclusive, determine the convergence or divergence of the series using other methods. Okay, so the absolute value of the a sub n is just going to get rid of this. And so that's just going to be 2 to the n over n factorial. So the absolute value of the a sub n plus 1 is to just go and replace your n with n plus 1. So that's going to be 2 to the n plus 1 over n plus 1 factorial. And so then we're supposed to take the limit as n goes off to infinity of the absolute value of the a sub n plus 1, which is going to be 2 to the n plus 1 divided by n plus 1 factorial, and multiply it by the reciprocal which of the a sub n, of the absolute value of the a sub n, which is n factorial over 2 to the n. And so then this becomes the limit as n goes off to infinity of same base, a base of 2 here and a base of 2 here. We can subtract the exponents and we're going to end up with 2. And for the n factorial over the n plus 1 factorial, we take the bigger one, n plus 1 factorial, and we break off factors, n plus 1 times n, but that's the same factorial that's up here, so we just stop and put n factorial, n factorial. Those cancel out, and now we have 2 over n plus 1, and we're taking the limit as n goes off to infinity, and this limit is 0. And again, this is not the limit comparison test. As long as your limit is less than 1, it converges. Okay. And then we have the root test. The root test, when you see powers, this is when you know when you see exponents of n, then you might want to use the root test. So the series a sub n converges absolutely when the limit as n goes off to infinity of the nth root of a sub n is less than 1. The series diverges when the limit as n goes off to infinity of the nth root of the absolute value of a sub n is bigger than 1, or if it's infinity, and the root test is inconclusive when the limit is 1. So again, you see this power of n right here. And so then that means that we might want to try the root test. So we're going to take the limit as n goes off to infinity of the nth root of negative, we're going to absolute value, so that's going to make the negative go away. It'll just be 3n over 2n plus 1. And then this is raised to the 3n. And so then the nth root of this to the 3n, again, if it makes it easier for you, you can rewrite this as the limit as n goes off to infinity of 3n over 2n plus 1 to the 3n raised to the 1 over n. Then when you multiply the exponents, you just get the limit as n goes off to infinity of 3n over 2n plus 1 cubed. Because the cube is a continuous function, you can bring the limit inside, and then you know what the limit of this is. That's 3 over 2. And then that gets cubed. But that's 27 over 8, which is bigger than 1, and therefore diverges.